Hi guys, just very quickly. So for setting up and recording these lectures, these labs, I've got the stupid camera setup that, well, not stupid. It's a convoluted camera setup that you guys have seen in previous images. Now, I've got a series of microphones that I use when I record, and I always try and check that they're working when I record because I don't want to have to re-record anything. So one of the shots in the laboratory that we're about to do has got two mics that are picking up the sound slightly out of phase, and it means there's a bit of an echo in my audio. Now, I've done my best to remove that using Adobe Audition. I am not re-recording this laboratory. It took me an hour to record. So I will apologize for that mildly unpleasant audio. I think it's all interpretable. If you have any issues with it beyond it's just annoying, let me know, and I'll endeavor in any sense to make sure that audio cock up doesn't happen again. Okay, cheers guys. Hi, good afternoon ladies and gents. We are starting out laboratory 1 for mechanical laboratory. This is really designed as an introduction to the kit that we're going to use and to teach you guys to understand the process of taking some physical quantities in the world and turning it into experimental data. So those are the didactic aims of this laboratory. When we write like scientists, we're going to say that in this laboratory, we are comparing the measured values of resistance for two resistors and comparing with the nominal value as indicated by the color codes. So those color codes for these resistors, we've got two resistors here. These are the ones that we're going to be using for this lab. It's not a particularly these cameras not particularly great at picking up all of those colors, so I thought I would just share nice big versions of the color code for you guys. So the resistor 1 has got brown, orange, yellow, then a gap, and then gold. Resistor 2 has orange, blue, orange, gap, gold. So these are the two resistors that we're going to be comparing in this lab. So we've got, let's call this resistor 1. And this one here is resistor 2. And so that's what we're going to call them from now. Your guys' job is to go and look at how we understand resistor color codes and determine the nominal resistance, including the uncertainty or tolerance of these two resistors. So I want you guys to look at those. This lab's going to be a bit jumping around between different things that I'm looking at. Just before I go and do any calculations, we're going to have a quick look at the kit that we're using. So let me bring this other camera up. Now, this is a slightly contrived setup. Normally, this desk would be set up for you guys. So I'm going to give you a look at what we're actually working with. Now, I obviously have to have a setup for recording. So there's a bunch of stuff here that you guys wouldn't expect to have, including a very lazy dog down here. Poppy. There we go. So she deigned to look at us. Let me just show you the things that we've got. So everything over here is just how I record these laboratories. But the piece of kit that we're using today, importantly, is the breadboard. Now, I've got a focus camera that will look on that when we're looking at it, but it tends to get oversaturated by the big white bit in the middle. So let's have a look at everything else. We've got a series of things that we don't actually use. So we don't use these down here. We're not going to worry about them too much. What the breadboard is primarily, it's a board at which we can make circuits. So each of these 5 horizontal pairs or horizontal sets are connected. So if I plug in here, it then is at the same potential as this one here. When we go vertically, these are not connected. In these vertical rows that have got 2 pairs, they are not connected horizontally, but they are connected vertically all the way down to here, where there's a disconnect, and then all of these are connected. So this will become clear, and I'll include a little diagram in the on the Slack space, just showing you how we actually use this. So there's the important stuff for us is that we can supply voltages. We can supply DC voltages using this system. So we've got a positive 5 volts, we've got a positive and a negative voltage, and these two are adjustable via these switches, these turns here. So we can have a range of voltages anywhere apparently from 0 to 1.3 to 15 volts between them. So 1.3 to 15 volts at each of these. So we can have a theoretical, if we're going between them, we'll have a theoretical minimum voltage of 2.6 going between these two, all the way up to 30 volts between these two. So we can then use those as power supplies for the actual circuit that we're going to be setting up, and then we'll put those resistors in, and we're going to measure the applied voltages and the current through them using these two multimeters. So the multimeters we spoke about in class, it's a device that is really useful because it helps us to actually measure lots of different things at once, including resistance. So you guys would check the resistance of these resistors using these bad boys in real life. So we see at the front, there's a dial which indicates which mode it's on. So we have off, we've then got AC voltage, DC voltage, we've then got millivolts, so I think this is for looking at thermistors. We've got resistance, we've got checking diodes, and then we've got the two current measuring. We've got milliamps and microamps. So the modes that we're going to be using primarily are this one here, DC voltage, and then this one here for current. Now we'll switch between these depending on the size of the current that we're looking at. And then depending which mode we're looking at, we always have a black and red cable connected to the front of these things. We always connect the common one to here. The black one always goes here. And we've then got a red one that can either go here if we're measuring voltage, or the red one goes here if we're measuring current. We also have it the red one here if we're measuring resistance as well. So this will become clear when I set it up, and hopefully we'll be having the camera here looking at these two outputs so we can use them as our voltmeter and our multimeter for this experiment. Let's get rid of the camera. Here we go. So we can, you guys can look at it, and I can keep both of my hands free when we actually set up the experiment. But the white tends to get oversaturated by this bit here, so you can't really see what's going on. And then when I actually run through the experiment, I'll keep a second camera on the two multimeters, so you can check the current through and the voltage across each of those resistors. So let's go back to the whiteboard a second. Takes me a while to get this set up, sorry guys. There we go. So we've got resistor 1 and resistor 2. Now you guys should be able to go and determine the two resistances of those, including the tolerance. I know what they are, so I know what voltage I can take them up to. Now that's really important for an experiment if we're using resistors. We've got to remember what a resistor does in principle. A resistor converts electrical energy into thermal, I'm going to put in brackets, molecular kinetic energy. So in other words, these things heat up when we use them. The resistor will heat up, and then that means that there's only a certain amount of energy that these resistors can dissipate per second. That's its power rating. So each of these resistors has a power rating. We just switch up here. I like to be behind the notes, not in front of them. So each of these resistors is only capable of actually converting a certain amount of energy per second, and that gives us the power rating of each of these resistors. So that gives us the power rating of the resistor. It tells us that if we try and put more energy per second through the resistor than that, it can't safely convert it to molecular kinetic energy, and it's probably likely to actually fail at that point. So remember, things get hot, they are likely to melt and smoke. So the first thing we're going to do is we are going to see what happens if we exceed that power rating for a resistor. So this is a 100 ohm resistor. I know this because of the color code. Moreover, I know it because I just pulled it out of the drawer of 100 ohm resistors. So let's think about how we can determine the amount of power that goes through this. So all of these resistors that we're using are going to be quarter watt resistors. I'm going to put up here, determine the power limit in volts, because that's what we care about. So all of these can safely convert a quarter watt, a quarter of a joule per second electrical energy into molecular kinetic energy. So this one is 100 ohms, and the way that we're going to be setting these up in the experiment is we're going to set them up on the breadboard, which I'm not going to bother switching to, and we're going to vary the voltage going through them. So we can vary voltage, we're going to be measuring current. We've got no real idea about the actual power that's being dissipated through it just yet. So we are going to use some equations that are going to help us. We know power is equal to I multiplied by V, or power is equal to current multiplied by voltage. We also know that V is equal to IR, that's just Ohm's law. So we'd like to have the power in terms of a voltage limitation. So we'll just rearrange this for I, and then this will end up being P is equal to V squared on R. So we've now got the power that's dissipated through a resistor as a function of the voltage across it and the actual resistance value. So this then tells us that V max is equal to square root of the resistance multiplied by P. We'll put the power limit on each of these. So each of these resistors is a quarter watt. So for our purposes, for the 100 ohm resistor that we have, so let's just put some values in here. This is for the test one that I'm going to do. This is not resistor 1, not resistor 2. This is just a test piece. That is 100 ohms. And with this one here is a quarter, so it's just 0.25. So this is therefore square root of 100 multiplied by 0.25, square root of 25, 5 volts. So what this is telling me, this is the maximum voltage I can safely and reliably take this resistor up to. And at values above this, there is a good likelihood that it will not withstand the amount of electrical energy that we're trying to convert into thermal kinetic energy through it. So let's set this up. Let's get rid of the iPad, and let's see if we can set this up as an actual experiment. So here we've got the breadboard. Now, the first thing I'm going to do is I want to be using these up here as my power supply. So I've got the positive and the negative. I showed you some good images of those earlier. Like most of you guys know, I cycle in, which is why I've often got bike grease on my hands. I apologize for that. So I am going to connect the inputs up to the circuit, and we're then going to be able to actually record some experimental data. Let me just go and find a jumper box. There we go. It's always good when I'm nice and prepared for an experiment and have everything else in front of me and I don't have to go wandering around the laboratory. So what I've got here, I've got a twin braided set of wires. This is black and red, and I'm going to use these to connect to the positive and the negative, just screwing underneath those terminals there. And I'm going to This is probably slightly longer than I need it to be, but I'm going to connect these two vertical lines here. So what this means is now that the red, which is connected to the positive terminal, is connected to every one of this vertical row here, and the black one, which is connected to the negative, is connected to every one of this row here, this column rather. So I can see that those colours aren't particularly easy to see on this, so my apologies for that. What I'm going to do is I'm then going to put the resistor. So this is a 100 ohm resistor, and we're going to pop this in here. So first off, I want to see how high this actual board will go in terms of voltage. That gives me an indication of what I'm working with and what I'm actually going to be looking at. So I'm going to get some cables that will go from my multimeter into the breadboard. Let me just set the cameras up so everything works. Let's put a little focus cam up there. Okay, so we've got that's my two multimeters. Going to use the cables at the front to connect a couple of survey probes. Now I want to record the voltage that I'm supplying to a resistor, and at the moment I'm not supplying anything, but I do know that the total voltage I'm going to be supplying is just going to be whatever the power into my circuit is. So I can then just put those into the terminals at the top. I'm going to put these wires behind the breadboard in a vein attempt to keep some tidiness here. I'm going to connect the black one to common, and then this is going to be my voltmeter. So I'm going to connect this one to the volts. I'm going to turn this to DC voltage. Okay, and it's telling me that there is no voltage that's present in the circuit. So if I try and turn these, nothing changes because there's a power button at the rear of the breadboard, which I can turn on. Thankfully, this one is plugged in. So if I now adjust these, this is probably not connected properly. There we go. I wasn't connected properly. So let's turn these all the way down to the bottom. The minimum voltage that I've got is 3.5 volts. Okay, which is a little bit larger than I was expecting, but that's fine. So let's turn this up. Let's see if I can turn this sound up. Very annoying. Why would you want sound up? Okay, that beeping is very annoying. Don't know how to turn it off. That's fine. So now what I'm doing is just altering the voltage going through here just to see what the maximum I take it up to. And if I overload it, I am going to This is actually a slightly different multimeter than the one that I use at the moment, so I'm having a little bit of trouble just getting the range of the set. There we go, so I've got a larger voltage now. It's because I've pressed that maximum button. Okay, so this will safely take me up to voltages. Yeah, we can go all the way up to 30 volts if I want. 30 volts of DC between these two terminals over here, which means that those cables that are coming in have connected up here and are now supplying these two columns with the two voltages that I had selected. So turn this right down, and then I'm going to turn this off. Now we're going to wire a circuit up such that I am supplying this resistor with that voltage. And I'm going to use that by connecting these jumper cables. So each of those tool boxes that you guys would have had have a set of These jumper cables, these are small cables that have a, it's difficult to see, let's put it here. Cables that have a plastic sheath over it, and then two actual bare terminals that I can just connect to. So I'm going to connect the positive, and that's going to be connected directly to one end of the resistor. So resistor's now got positive excitation. And then I want to complete the circuit, but I need to complete the circuit in a way such that the current also goes through what's going to be my ammeter. So let's connect this ammeter up. So I'm going to put the common terminal here, and I expect this to be milliamps. So let's put this over here. Turn it to milliamps. Now what I'm going to do is I'm going to connect one of these, which are little push terminals. I'm going to connect one directly to the arm of the resistor, and I'm going to use a small cable just to return this back to the input voltage. So if I now connect this, there we go. So this is my circuit set up. So we've got a 100 ohm resistor through here. So let's turn this on. And remember that both of these voltages are down nice and low. Let's just see if we get out something that makes sense. Okay. So when I turn it on, the lowest voltage that I get through is 2.8 volts and 0.1. We got sort of a voltage. It's not quite steady. It appears to be going down a little bit. That's fine. And we've got a low current coming out. So let's just see if these numbers make sense. So my resistance is 100 ohms. My R is 100 ohms. My V for this is 2.81. So I is equal to V divided by R. So that's going to be equal to 0.028. Okay, and that's close enough to what we've got coming out here. Slightly lower than we'd expect, but we're close enough for the purposes that we're looking at. So remember that the power limitation that I said we could take this up to, the maximum this can go to was 5 volts, wasn't it? 5 volts was the supposed maximum that we should be able to put across this resistor, and it should be able to safely dissipate that. So I'm going to increase the voltage and see what we get coming out. So I'm going to just increase this up. Oh, I'm measuring AC current. That was why that current didn't make any sense. There we go. That was a stupid mistake. So this is now measuring in microvolts. No, that's wrong. That was okay. There we go. This button here switches it between AC and DC. That was my mistake there. So let's just go back down to the minimum. There we go. So that number's actually much better. So we've got 2.7 volts going in, and we've got 27 milliamps, and that makes sense because that's this number divided by 100 to get this one. Okay, that was my mistake with setting up how this works. Let's now increase the voltage up to 5 volts. So this is supposed to be the maximum that this resistor can take. I'm just going to get ready to move this camera because I might want to just move it and show you what happens to the resistor. So I'm just going to keep the voltage being shown here, trying to eliminate the camera glare. Let's increase the voltage so I can feel. That is warm to the touch. Probably shouldn't touch it like that. Okay, we've now got 8 volts. See if I can get double. Okay, so we've got 10 volts going through here, which is just over double the theoretical maximum for this resistor. So that's pretty warm. Let's turn this up. I'm expecting it to start smoking at some point. Oh, it is smoking now. Here we go. So it's giving off lots of horrible plastic fumes. I don't want to do this for too long. You should be able to see that this resistor is burning up. Okay, so this resistor is burning up because it's no longer able to take that through it. We've gone to 3 times the power limitation here. So let's turn this off. We've no longer got any application going through it because that plastic smell is horrid and probably not good for me. So that's why we need to look at the power limitation of resistors, because it's important for our purposes to understand the maximum voltage that we can take them up to. So for those 2 resistors you guys have got, which is resistor 1 and resistor 2, you need to determine the maximum the maximum voltage we can take them up to. So what I'm going to do is I'm going to keep this circuit set up the same, and I'm going to switch between those 2 resistors. I'm going to just put a new resistor in, and I want to record a series of voltages, and then record a series of corresponding currents as well. So let's turn this right down. Breadboard's off anyway, and all I now need to do is take out this jump resistor. This one's going to be thrown away because it's all burned up. Let's see if we can see that. It's all burned up. So we can get rid of that now. Okay, so I'm going to connect this is resistor 1. I'm going to connect it here. Doesn't matter where I put it in because the circuit's being completed through the ammeter. Here we go. So just in case we're at all confused about the way this circuit works, so what we have is we've got a DC power supply. A DC power supply has got a symbol like that. We've then got our resistor with the known resistance. We've got the ammeter, which is connected in series, and then we're also measuring the voltage. So those are the different parts that we have. So this voltmeter here is connected across, and it's connected across because we've got these 2 cables just connected to the power supply. The ammeter is connected in series, and that's because it's taking the circuit effectively is powering up or it's providing the positive voltage to the resistor, which is coming out the other leg, and then the circuit is being completed out of this cable, which goes into here, measures the current, and then comes back out here, which is connected to this rail, which takes it all the way to the power supply. So this is our circuit that we've just developed, and we're going to be using it again with different voltages. So what I want you guys to do is to record a series of these voltages in and the corresponding currents that we get through the whole process. So let's just keep focus on these 2 here. Okay, that's pretty good. Look there. I'm just going to try and... No, those look good, I think. That's good. That's a good look. So we've got the circuit set up. We've got resistor 1. And I want you guys to record these data in a suitable table. So, for example, resistor 1. We're going to record a series of readings. So that'll be the number of the reading that we've taken. Recording the voltage and recording the current out. So I'm going to record these as milliamps and volts. So I'm going to look at the numbers that are directly coming out. This is a voltage in volts. This is a current in milliamps. So Now, with nothing going through it, it appears there's a small amount of some current that's getting from somewhere. We don't need to worry about that too much. So we can safely say that we know that reading number 1, we've got 0 voltage and we've got 0 current. So let's turn this on, check these are down low. Here we go. So first reading is, let's see if there's a way I can move this a second. Let's put this down there. That's better. Okay, so the first reading, the first proper reading, I should say, we get 2 the voltage. Let's call that 2.7. It's not particularly stable. Let's call that 2.78. I'm only going to record to 2 decimal places because that's all I can really be confident with. We can see that it's fluctuating around. That's just a consequence of these breadboards don't have a particularly stable power supply. It appears to be drifting quite a bit, but I'm not too worried about it for the purposes of this experiment. Okay, and the corresponding voltage is 0.04. Okay, I'm going to increase this. Now, in the lab instructions, originally for this lab, it said go up in approximately 1 voltage steps, or steps of 1 volt. So you see students, right, so this is at 2.7, so I'm going to very carefully go up to 3. No, it's 3.6. Let's go up to, no, that's I mean, that's actually very good that I managed to get 3.7. But what I'm trying to hit here is that it doesn't really matter what voltages we actually go up to in terms of how precisely we take those steps, as long as we record them properly. So I would have just gone, okay, that's a little bit higher. Yeah, it's 3.2. Okay, so let's say our third voltage. Let's turn that up a bit because this has come back down again. I might need to get this breadboard looked at. Definitely need to get this breadboard looked at. But let's say this is 3.09 and 0.04. I'm just checking this is actually working. Okay, the first reading I would trust. The second one, let's take the voltage up to 3. I'm going to take this reading again, so I'm going to get rid of that one. Let's call this number 3 is 3. I don't trust this multimeter, so I'm going to grab a multimeter to replace this one with, see if I can get a better reading out. There's every chance I'm not using that multimeter correctly. This is not a brand I've used before. This is the one that I tend to use. It's one that I've got at home. So let me change this to measuring current, and I'm just going to switch this left one out. I'm confident that voltage is correct because they look like it's changing with the voltages I'm changing. I'm just going to see if this gives me a different current now. No, that's probably fine. I think it's so, the numbers are so small that they're moving about. Okay, so let's try and take that third reading again. Let's just go to the next reading. I've called this 3.11. And then again, I've got 0.04. It's quite a high resistance in this resistor, so let's take this up. So that's quite a big step up. I know the power limitation of this one. You guys should have found it out to find, but I'm probably not going to hit it with this breadboard. So I've got 4. That's reading number 4, 6.13 volts, 0.06 milliamps. I'm going up in slightly larger steps because I've got a larger resistor. Let's do 5, 8.45 volts, 0.08 milliamps. 10.58, 0.10. Reading number 7, 13.14, 0.12. 8, 15.73, 0.14. 18.99, 0.16. You can probably see I'm just trying to go up in steps of about 0.02 milliamps. So let's call this 20.53 volts, 0. Let's round that up. 0 points. No, let's not. Let's call that 0.17. Okay. Turn up to the other dial. Let's go up a bit more. 12, 29.16, 0.24. 37.58, 0.31. That's the last one. This is as high as the voltage goes to. It is higher than it says it can do on the breadboard, which is interesting. 40.03, 0.33. So you guys should be recording those as well as we go through this. Those are going to be the data that you want to look at in this first resistor graph. So let's go back to the whiteboard, away from the breadboard onto the whiteboard. Okay. There we go. So these data that you guys should have a copy of they are the first resistor. So those are the the voltage across and the current through. Now, what students sometimes tend to do is they think, well, V is equal to IR, R is equal to V on I. So what I can do is I can get R, V on I here, and then so I've got 0 divided by 0, which is meaningless anyway. You then calculate this, so it would then be 2.78 divided by 0.04, and they would repeat that down the whole column. Now, I'm only highlighting this to say, don't do that. That's not something that we do with this sort of experiment, because when we first powered up, we assumed we had 0 and 0. We actually saw that when I've got nominally no voltage going through here, there's no power into this breadboard, there's some sort of, let me just bring this back up. So even though I've got nominally no power going into this whole system, it's still registering a small voltage and a small current. And that's probably just offsets within the measurement devices themselves, perhaps some small voltages leaking through from the earth or ground, or possibly there's some parasitic thermocouples somewhere in here that's causing those small voltages to arise and small currents that accordingly arise. But the reason I'm bringing that up is because if you then were to do what I said don't do here, you calculate erroneous voltages. So what we do instead is we take all of these numbers, and you guys are going to plot them on those scatter graphs that we spoke about. So we would put V on V, I on A, converting milliamps to amps. Now this is maybe slightly the other way around to how you'd expect to do them. We're taught often to put the independent variable on the bottom, that would be voltage, that will be varied, and the dependent variable on the ordinate, which is for our purposes would be the current. But because when we are getting the slope of the curve through here, if we do it this way around, the slope of the curve will be the resistance. So you guys are going to put your points on here, and then determine that line of best fit through them. Then the dy on dx equals the resistance if we do it this way around. If you do it the other way around, you have to use the reciprocal of the resistance. So the reason why we don't do it this way around is because that small number, if we have a small number at the beginning, which according to the camera here is about 0.01 of a milliamp, and a small bit of voltage, you'll get an offset here. Okay, so that offset is taken into account by doing this process, doing this procedure. What we end up with here is the rate of change of the current through the resistor with the rate of change of the voltage, and that by definition is the resistance of this resistor. So you guys are going to do this, and I then want you to be able to plot the nominal resistance on here as well. So this is then the measured, and I would expect the nominal to be pretty close to this, so you might want to have nominal as well. I go through this in those YouTube videos for the MME 100 class. I do a very, very similar, I think I actually just did the data reduction for this class in that video, so you guys should be able to do that. Okay, so I've done that set of readings for one resistor. I'm going to go and put the second resistor in here now, resistor 2. I'm not going to write down those voltages. I'm just going to go through and I want you guys to read them as we're doing it and then comment thereupon. Okay, so I have forgotten which resistor I have plugged in. Let me get the camera up. Okay, so this was resistor 1. Let me just swap it for resistor 2. Okay, yes. Resistor 2. Taking resistor 2 out, popping it back into the circuit, and connecting the. There we go. So we've now got resistor 2 in here. I'm going to do the same thing, take it up to high voltage. I know that the maximum voltage that this one could take is quite a bit larger than 40, so I can take this all the way up, and I'm going to get you guys to do the same thing, record those voltages that we go through. So this would be the first real reading. We've got 2.684 and a and a current of 0.09 milliamps. Let's just take this up in steps. That can be a second one. Third. Fourth. Fifth. Sixth. Seventh. Eighth. And that's the limit on the left hand knob, so let's turn this up a bit more. 9. 10. 11. 12. 13. And 14. Okay, so those are the readings taken with the second resistor. I've not written them down because I don't need to. You guys have got to go through and check each of those, write them down and do the same thing that we just did, or the same thing that you would have done for this first resistor here. So let's get rid of the equipment a second. Let me just turn this off. Okay, so what you are going to have to produce for this, there'll be a Blackboard quiz which is going to walk you through a lot of the actual talking about this experiment, because you're not submitting a lab report for this one. It's too simple. I'm not a big fan of doing 1,000 lab reports in a course. I'd rather you did a few good ones. So we're going to talk about. So remember, we had introduction, method, results, analysis. These are often actually just together, and then discussion, and I'll also put conclusion at the end as well. So we've got the way that we're going to talk about this. Remember that for our introduction here, we sort of set the scene. I will do the writing for this part. You guys have got to pick the right words at different points. But just remember that an introduction should always have the aims and expectations. And remember that with our aims, we're talking about scientific aims. We're not talking about the aims of you as a scholar. We're talking about the aims of doing this experiment. So the aim of this experiment is to experimentally determine the resistance of two resistors using Ohm's law and to compare them with the nominal values as determined by the color code. We expect those values that we determine using Ohm's law to be close to the nominal value and within the bounds of tolerance. And those bounds of tolerance that we get are determined by the color code. So that's our aims and our expectation. The method for this method was simple. We set up one circuit on the breadboard that enabled us to put a resistor, supply a voltage across, and measure the current through and then the voltage across it. And that's where I want a nice circuit diagram. I'll draw this circuit diagram and include it for you in this one, but I would expect you guys to be able to draw your own circuit diagrams. So the circuit diagrams, if you don't have a good graphics editor on your computer, just look up Inkscape. Inkscape's really good. It's free, it's cross-platform, and it enables you to do vector diagrams of different things. It's good for doing circuit diagrams. If you're a LaTeX person, then look up TICS and something called circuit TICS, or circuit TICS, I guess. Okay, those are different ways we can draw circuit diagrams, or you can just Google, how do I draw a circuit diagram? And it'll take you to one of the many online generators that enables you to do it. The results, this is where we have 2 times tables of those voltages, tables of those currents, correctly laid out as we spoke about. So no vertical lines, and then in the column headings I want the units non-dimensionalized by those units. So the quantity non-dimensionalized by the units and not putting the units in brackets. And then I want 2 times graphs. So those 2 graphs should have I've drawn a massive offset on here. It won't be that big in real life, so we'll draw them like this. So we're going to put two different curves up here. You're going to put your data, you're going to do a linear regression, which is going to give you an equation out of the form v is equal to I multiplied by r plus delta v. And this is just now a small offset that we have wherever it intercepts down here. You're going to get r, you'll determine the resistance from it using that line of best fit, and that's what the line of best fit's purpose is. It's there to help us get it. We're also going to put a nominal resistance on it. So if the nominal resistance of one of those resistors was, say, 130 kilograms, you'd put an intercept of 0, you pick your maximum voltage, maximum current, you'd probably just pick the maximum voltage, divide it by your nominal resistance, and that gives you your maximum current. And draw a straight line joining those 2 points. That is your nominal behavior. And this is a good way of indicating how closely these two tie together. What you can also put is tolerance bounds on the upper and lower. Okay, so we'll put the tolerance bounds on there. If you've managed to put those on there and they're done correctly, I'm going to consider that as a small extra credit thing. Okay, that's just good data presentation. That really clearly would show you on a graph that your measured resistance is within those tolerance bounds. Okay, so I expect this one, and this one on everyone's graph. This one is on those Python WizKids graph. Okay, I don't want to see any Excel graphs. Excel is not suitable for a job such as the ones that we're going to be doing. Okay, you can just about get away with this graph in Excel, but it's not really what it's designed for. Excel is a great tool for accountants. It's not particularly a great tool for engineers. Also here, see that even though I've just drawn this, this has got a suitable scale on it. So make sure that your actual lines fill up your entire graph. I don't want to see graphs that are submitted that look like this. Okay, if you have a graph and you've got all of this excess space in it, that's not any good. So you're going to submit 2 of those graphs, and there'll be a space on the Blackboard quiz where you're going to upload them, and there'll be a rubric that the TAs are going to use to see whether you've done all these things. So remember, axes labels have to have the quantity, and it has to be non-dimensionalized by the units. We're going to put them in SI no prefix units. So we've got amps in here, and we measured in milliamps. So you've got to figure out how to convert between amps and milliamps. I would hope that by third year you guys could do that. Analysis, there isn't really an analysis in these. They're sort of just joined together here, okay? So you can then compare a small bit about, at the end of this, I'd probably also just like to see 2 times measured resistance. Okay, so 2 times measured resistances. There'll be spaces in the Blackboard quiz where you're going to put it in, and it's there so it sort of reads like a report for you. Discussion. Did the results match your expectations? Why or why not? Okay, so we'll say, yes, the measured resistance was within the bounds of uncertainty as indicated by the nominal resistance of this resistor. That's to be expected. That's good. If it's not, we can start to think about reasons perhaps why not. Conclusions. An experiment was performed. Did you meet your aims? Okay, so our aims were to compare the measured resistances of 2 resistors and compare them with the theoretical, the nominal resistance as indicated by the color code. So if we do that, then we'll see an experiment was performed to do this. Great, that's a good conclusion. Okay, so there'll be a Blackboard quiz available for this when I get around to writing it, probably by the end of the week. Your job primarily is producing these graphs. Okay, remember we want to see nice big graphs with all of the things that we spoke about that should be in a graph. I'm going to include a link at the end of this video to the salient Python instructional video that I effectively do all of this work in. I did it as an exercise for the first years last year, should help you guys with it. Okay, so I hope this has been informative, fun, exciting, and electrifying. And I will see you guys all next week. Take care.